So in this video, I will derive the Euler-Lagrange equation for Lagrangian composed of a function of any finite number of higher order terms, of multiple input, single output functions for any number of inputs. The solution I derive, however, will work only if we enforce a particular set of boundary conditions that I will soon describe mathematically as one of the simplifications. As in the previous two videos I made about the Euler-Lagrange equations, the goal is to find the y of x that optimizes the functional j of y. We will call this solution y hat of x, and note that x is a row vector of variables, and thus the Jacobian derivatives of y with respect to x are all column vectors. So in order to optimize j of y in our, I guess you can call it function space, we're going to add a perturbation to y hat. So basically we're going to say that our function is a vector in infinite dimensional space. We're going to say, like, okay, we're going to create the epsilon axis starting at y hat and going on in the direction of eta and scaled by epsilon. So theoretically, if we take the in any direction, we want the derivative with respect to epsilon of j of y hat plus epsilon eta to be equal to 0. So that means that in all directions in function space, the derivative is 0. So if we substitute in the j of y into the equation, then we get this. All of that is equal to 0. Oh yeah, sorry, I forgot to mention that we're evaluating everything at epsilon is 0, because at epsilon is 0, we have y hat in our epsilon axis. So now what we're going to do here is we're going to define z to be a column vector, meaning that this all becomes a column. So basically x is now like a column vector, and the Jacobian derivatives are now they're row vectors now. So that's just an important distinction that will come in handy soon. All right, and now what we can do is that we could aggregate all of that as a z column vector, and we're evaluating epsilon is 0. We pull in the derivative operator into the inside of the integrals, since the integrals are just an infinite sum. Then we express this derivative as the Jacobian chain rule. If you're not familiar with the Jacobian chain rule, then I encourage you to look up my video on the Jacobian chain rule. So then we get this. We get this this row vector multiplied by this column vector over here, and they're all evaluated at epsilon is 0. And that's all going to be equal to 0. Now, one thing I forgot to mention on the previous slide is that these I'll be using these gradient operators. This just means that you're taking the Jacobian derivative with respect to x of y hat, and the superscript represents the degree of these derivatives. So in this case it's 1. In this case you're taking the nth derivative with respect to all the x's of y hat. And over here, just taking the derivative L with respect to x vector. And over here, you're doing the same kind of gradient thing, except it's with respect to eta, which is our the direction of our axis in infinite dimensional space. So then we take the dot product, or we do a matrix multiplication, and then we get this. And let's see, did I do here? Oh yeah. So in between these terms, we'll actually get something like this. We'll get the mth term, and what this mth term is, sorry, we could actually distribute the integral throughout all the terms. And then now let's just focus on this mth term. So yeah, let's do that next slide. Let's focus on trying to expand it using the chain rule. I'm sorry, not the chain rule, but the integration by parts. But, how do we do integration by parts on this thing over here? If it's multivariable, well, I'll show you. So on this slide, this becomes this over here. Well, it doesn't become that. It's just another way of expressing it. I just express the, I just switch notations over from here to here. It's still the Jacobian derivative with respect to x. But this is the mth term that I want to focus on in the previous slide. And we're going to try to expand it. So we're going to say that this part is equal to a. And if that is the case, then we can take the, then if we do the sum all the multiplications of each and every one of these terms, what we're doing is the matrix multiplication. We can say, okay, the sum of all over I of the ith components of a and the ith components of this Jacobian derivative of eta with respect to x dx over the integral is equal to this by the chain rule. I'm sorry, not the chain rule, the integration by parts. Yeah, you just keep this term as the higher ordered term, and you take the integral of this term. I just said the integral of this term is b sub I 1. It's because you're taking the integral of this term is over these boundaries of x1 and x2, where x1 and x2 are actually vectors. I didn't mention that, I forgot to. And yeah, that's the integration by parts. So if you keep on going, if you keep on integrating by parts, you're going to keep on getting these boundary terms, which is just like these ai is multiplied by the b sub I k. And we're going to do this all the way to the kth term. And if you keep on going all the way to the mth term, then you get m minus m. That's equal to 0. And the zeroth derivative of eta with respect to xi, that's just eta. So, and then the mth k becomes m. So you're just doing, just writing m over here. And yeah, that's the expansion of this, the integration by parts in general. This is just the single variable integration by parts, but we're doing it element-wise. You get this negative 1 over here to the kth power because you're always going to be subtracting. So, you get negative, then positive, then negative, then positive. It's just alternating. And yeah. And so, we obtained this expression in the last slide. And we can say that the sum over I of all of this on the left side of ai times xi, that's just the vector a matrix multiplied by the gradient. That's why you get that sum. So this is just another way of saying this over here. Then we get those boundary terms, and then this term could be written as this, where you can factor out that negative 1 to the m, you put that summation into the inside, and you pull it in again. And then what you get is that when you pull in that summation, you'll see that it's just the sum of the of all the elements within the gradient vector with respect to x, and that's divergence. That's del dot a. So what we've done here is that we derived the multivariable integration by parts, and this is a very powerful concept. And so yeah, it's just the dot product between these two vectors is equal to the divergence between that stuff right there. So now for all these terms that I'm circling, we have an expression for each one, for each of these integrals in this summation. And that is, if we say that this is a, and this is this term, then we have, well, all of this is equal to the divergences. If we assume that the boundary terms for each one of these integrals sums to 0. So that's a very important restriction that we impose to get to our final solution. So then if we substitute in everything, we don't substitute in anything for the first term, but we do for the second, third, all the way up to the nth term, well, technically the n plus 1th term. And that's because we can expand those 1 to n terms through integration by parts, the multivariable integration by parts. And if we just write this as a summation, then we get this. And we're factoring out the etas. We're saying eta times all these integrals. But all those integrals are just summations, so we just pull out the integral, and we're left with this term inside here, multiplied by eta, and the integral from x1 to x2. This is actually like multiple integrals. This is like the integral from the integral, the integral, the integral, the integral, however many variables are in dx. I don't know how many. It could be anything, really. So yeah, that's the expression we obtain. So if we apply the fundamental lemma of calculus of variations, I forget what it is, but it just means that if you have this function multiplied by this function in the integral over that, then I think it means that this must be 0 because of something about eta. I'm not really sure why, but I guess you can look it up if you want to, or I can make a video on it. But yeah, this term over here must be 0. So that means that we get this as the Euler-Lagrange equation, the solution to y hat of x is equal to the argument of y of x of j of y. We're finding the y that optimizes the j of y, expressed as this functional. But remember that it's subject to these boundary conditions that we imposed on each and every one of those integrals that we added together after we expanded them through integration by parts. So we were just left with the term on the rightmost term, and the left terms were just those boundary conditions. And yeah, that's we got the general formula. That's pretty cool. All right, that's it, and thank you for watching. Yeah, see you later.